webinar is Building Your Optimized VOC Method, presented by Amy Nutter, Applications Chemist for Teledyne Tekmar. We will be taking questions, so please submit your questions throughout the presentation, and we will address them at the end if time permits. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Amy Nutter.
Thank you, Shelley, for the introduction. Like she said, I'm Amy Nutter, Applications Chemist here at Teledyne Tekmar, and today I will be discussing how to utilize the tips given in the Method Optimization series and the Moisture Control webinar in building your specialized VOC method. We will cover a quick overview of the Purge and Trap technique and our products, specialized applications and how to build your optimized method, and why we use certain parameters and how they help with the analysis. So we have a lot to cover today. Let's get into it. Now let's get into how Purge and Trap works. The theory of purging and sweeping the sample with an inert gas is called dynamic headspace theory. It sounds simple, but is a very complex process. Purging a sample to extract analytes is a gas extraction. In purging the sample, the system is no longer at an equilibrium, and this is because the VOCs that move into the gaseous phase are constantly being removed by the purge gas. Continuously replacing that headspace causes a disequilibrium, in that there is always a higher concentration of VOCs in the liquid phase than in the gaseous phase, creating a net movement of VOCs from the liquid to gas, extracting the VOCs from the sample more efficiently and improving on sensitivity. Then the gas is swept away onto the trap where it has been concentrated and released to the GC. A basic purge and trap consists of 5 main parts: the sparger, flow control, 6-port valve, analytical trap, and heated transfer line. The sparger is the glassware on the front of the instrument that receives the liquid sample to be purged. Purging the sample extracts the VOCs by dispersing inert gas through the sample matrix for a preset time and flow. This flow is controlled by a mass flow controller or a pressure regulator that monitors and precisely controls the gas flow rates throughout the entire purge and trap process. From there, the 6-port valve directs the gas containing the analytes to the analytical trap for concentration. By backflushing carrier gas through the analytical trap, the 6-port valve directs the VOCs to the GC for separation and detection. The analytical trap is used to capture and release VOCs swept out of the sample by the purge gas. Trapping the VOCs helps create a smaller band of analytes traveling to the GC column, producing greater signal-to-noise ratios and lower area-to-height ratios, generating sharper peaks and better sensitivity and resolution. Once the VOCs are captured, the trap is heated, causing the VOCs to desorb, and carrier gas is used to desorb these VOCs off the analytical trap and carry them to the heated transfer line into the GC. Teledyne Tekmar is the market leader for purge and trap in our nation, and we offer several different options. The Lumen Purge and Trap concentrator, shown on the right, is our standalone waters-only concentrator that can be paired with the Aquatech LVA auto sampler. And we also have the combined auto sampler and purge and trap concentrator, the Atomx XYZ, shown on the left, which is capable of analyzing soils, solids, and water samples. Many of these non-traditional methods have little or no government-mandated methodologies for their analysis. So unlike traditional EPA drinking water or wastewater methods that are standard across all laboratories all over the country, and this is done just so that drinking water and wastewater meet a certain criteria are standard no matter where you are. Often, these non-traditional analyses, there's like very little published guidance on how to run these applications. So most of the time, applications have been converted over from one of the more traditional analysis technologies like headspace or solid phase microextraction, SPME. So what kind of parameters can we borrow from these applications that would be beneficial for our purge and trap method? Maybe like sample volume, sample temperature, or trace level analysis. Some method development may be needed. Therefore, in this webinar, I want to walk through developing an optimized, specialized method, including explaining why certain parameters are chosen and how they can help your application. Today, we will cover 4 specific non-traditional environmental applications: molten odor, Wisconsin GRO, 1,4-dioxane, and epichlorohydrin. Taste is becoming an increasingly important aspect of water quality. Detecting and eliminating molten odor compounds is critical to water suppliers. So when we say molten odor, we're talking about 2 compounds of interest, jasmine and 2-methyl isoborneol, or MIB. These 2 contribute to the musty smell of finished drinking water. They don't pose a human health risk that we know of, but humans have an extremely low threshold for these compounds, odor threshold for these compounds. So we're talking in the PPT range, which means when you smell that musty, moldy, just rain smell in your water, you assume that the water isn't safe and you don't want to drink it. Since we can smell in the PPT range, we need really low detection, which further complicates the fact that these compounds are poor purgers, and that creates challenges when setting up these applications. So for method development of this application, we want to focus on 3 areas. We need to improve the purge efficiencies, optimize sample energy and mass spec sensitivity, and we need to clean up our sample pathway to ensure no carryover issues from sample to sample. This molten odor method was built and ran on the Atomx XYZ, but since it is a water method, it can be ran on the Lumen as well. Or if you have some of our older models like the Atomx or the Stratum. But remember that the Atomx and the Stratum do not have the same moisture control system as the Atomx XYZ and the Lumen. So you may need to add in some extra moisture control parameters for those systems. This is the first tab when you open up the water method to build your water method. This is a standby tab. Here, we would just like to lower the sample mount temperature to 60 degrees C, and this is to help a little bit with that moisture control. All right, next we have the purge parameter section. So we're talking sample volume, if we want to use a sparger heater, dry purge, these are the parameters that we want to change. So one of our focus areas in this method was purge efficiency. So purge efficiency includes sample volume, how much sample we are going to start with, purge time, so how long we are going to bubble our purge gas through that liquid sample to strip out our compounds of interest, purge flow, which combined with purge time gives us the total amount of purge gas that we use. So the more purge gas that we use is going to strip out more of the compound. However, it also strips out water. So with compounds like jasmine and MIB that are have poor purging efficiencies, we're going to remove a lot of water at the same time. These molten odor compounds are broad. They're more like semi-volatile compounds. They're large and sticky, and they're hard to purge. So we want to use that 25 mil sparger instead of a 5 mil sparger, and we want to purge a 20 mil sample. The larger sample volume and applying heat with our sample vessel heater, our sparge vessel heater at 60 degrees C, will help drive those compounds out of the water phase and into the gas phase. But there are some trade-offs here regarding adding additional moisture. So an increase in sample purge temperatures always increases the purge efficiency with which VOCs move from the liquid to the gas phase. But the trade-off is the amount of water vapor that makes it onto the trap doubles for each 10 degrees C rise in sample purge temperature. So to help with this extra moisture, Tekmar has focused a lot of effort into improvements on our moisture control by creating the improved moisture control fitting and this is available on the Atomx XYZ and the Lumen. Dry purge also helps. So dry purge is the flow of clean, dry gas through the analytical trap just before desorb to remove moisture. Typically, the larger volume of dry purge gas that we put through our system with a high flow rate, or the longer that we dry purge, we're going to remove more moisture. So this would be especially important if you have those older systems like the Atomx or the Stratum. 2 minutes of default, or 2 minutes of dry purge is default here. So we just want to stick with that. Up next, we have our Desorb parameter selection. These are default parameters for the K-trap, but Desorb can be a really important step in removing moisture, especially at the low levels we are trying to achieve with this method. So we can adjust our desorb time to help reduce the amount of moisture that we put onto the GC. So a longer desorb time means we are going to remove more of those compounds from the analytical trap to the GC. So we will be improving on analyte recovery, but that also includes water that may be in there, which will give us, a longer water peak. If we shorten the desorb time, we move less of that material to the GC, and we will have a shorter water peak. This gives us a little opportunity for optimization, both in the length of our desorb and also the temperature of our desorb. So a rapid increase of temperature during desorb preheat can drive moisture out of the sample, and the final temperature of desorb ensures that the moisture stays out of our gas flow and that we transfer everything to the GC. So these are default methods that we see here. And this is the same desorb tab, but with parameters for a 10x trap, which is the recommended trap for this analysis. If you're just specifically doing this analysis, we recommend the 1A trap or any kind of 10x trap. So the data that I'm about to show you for this method was created with the K trap. So that's why I wanted to show you the parameters before. But as far as trap selection for this method, it really depends on how many samples you're running and how often you are running this method. If it's not too often, maybe once a week, you could try using the K-trap or whatever trap you use for your everyday analysis and see if that works for you. It could save you a lot of time and resources using one purge and trap for all of your sample analyses. So the 10x trap uses different temperatures, but has the same idea. Always be sure to follow the correct conditioning parameters and method parameters in your trap guide that comes with your trap. You want to make sure that you don't overheat the packing material, causing a breakdown of the adsorbents. And the reason why we recommend the 10x trap, specifically the 1A trap, is because not only are these mold and odor compounds really big and heavy, but once they're on the trap, they can be hard to re-release. and cause carryover, trap fouling, and back pressure issues. And the 10X trap aids in the re-release of these compounds because of its large mesh size that resists fouling and back pressure issues a little longer than your standard trap. All right, and here we have the bake parameter selection as our last tab in building our water method. So bake removes all the moisture that we have accumulated in our system during the purge and trap process out of our system so that we can continue to remove water from sample to sample. And our bake out also helps with preventing carryover. So carryover is any time that we see our compounds of interest moving from one sample to the next. For example, seeing target compounds in a blank following a high concentration sample. So why is carryover so bad? It contributes to a loss of productivity and a loss of sensitivity. So when we have carryover, we have to spend more time cleaning, more rinses in the purge and trap, leading to longer run times and less sample throughput per hour, or time spent by the analyst troubleshooting and repairing contamination issues. There is no real specific EPA method requirements for carryover and few suggestions for cleaning systems. So how much carryover is too much? We like to suggest that blanks after high concentration standards should be below your MDL. So what we do is try to select method parameters that both minimize carryover and minimize sample runtime. The temperature that we use for bake is dependent on our trap. So we want to make sure that we don't overheat our packing material, causing the breakdown of the adsorbents. Areas of optimization here would be the length of bake and the temperature. So with our improved bake mode control, we can create faster flows and higher temperatures, which means that we can bake for less time, saving extra time per sample, and improved trap cooling leads to less downtime between samples. So making sure that we get hot enough and our bake gas flows through the trap for long enough to remove all of that moisture without going for too long. A good bake gets all the water out of the trap and the moisture control fitting to make sure that it's ready for the next sample. And that's why here we would like to see a larger volume of water for our bake rinse. Just because we used a 20 ml sample, we want to make sure we use enough water to rinse that entire sparger and ensure that it's clean for the next sample. And we want a long bake out of the trap just to ensure we're removing any leftover sample, because just those compounds like to stick around. So we want to make sure we get rid of them to prevent carryover. Same bake tab, but these are the 10X trap method parameters. So it would be a different bake temperature so that the trapping material doesn't degrade. All right, lastly, not just through the hardware that we have designed, but through smart method parameters on the GC side, we can control the moisture and improve analyte recovery by using shorter, narrow bore GC columns, and we can adjust our split ratio. So a higher split means more of that desorbing gas coming to the inlet going off to vent, and less of it is going onto the column. A higher split ratio means less water is going to go into the inlet and onto the column, but that also means that less of our target compounds are going there because they're going off to vent as well. So if we have our split ratio set too high, we will start to lose analytical sensitivity. The less water going onto the GC column means less water that's getting to the mass spec as well, and this can extend filament life and allows for less source cleaning, which is a huge time saver because that's a long process. With this method, we want to lower our split ratio to put more of those compounds onto the column, allowing for more of it to make it to the mass spec. As long as we are getting good recovery and area counts that adequately calibrate, and we're seeing a reduction in water from our other parameters, what we have selected should be all right to lower that split ratio. Selected ion monitoring, or SIM mode, is a mass spec scanning mode, which is only a limited mass to charge ratio range is transmitted and detected by the instrument, as opposed to the full spectrum range. So this mode of operation typically results in significantly increased sensitivity. So here we have the ions for both MIB and Jasmine and the internal standards. The gain is the number of electrons generated for every ion that strikes the detector. The detector gain is relative to multiplier voltage. So if the detector gain is increased, the multiplier voltage will also increase. And higher gains give larger signals, but may shorten the lifetime of the detector when concentrated samples are detected. The gain is typically set between 1 and 3 times 10 to the 5th electrons per ion, and gains larger than this will generate more electrons per ion, but both the analyte ion and the noise and signals will be larger. So here we have a higher gain to create larger signals to see those low levels for our low-level analysis. All right, here we have the MIB results, so extracted ion chromatograms for our 50 ppt MIB, showing the quantitation ion and a confirming ion, and a linear calibration over the concentration range of 2 ppt to 100 ppt, resulting in a 0.996 R squared. And here are the Jasmine results. Again, we have a 50 ppt showing our quantitation ion and then 2 confirming ions, and the linear calibration over the range of 2 to 100 ppt at 0.998. So here, purge efficiency was improved using a large sample volume, 20 mils, and heating, all while maintaining adequate moisture control. We got enough MIB and Jasmine out of solution, trapped, and then moved to the GC. Our split allowed for excellent calibrations, low insensitivity, and we helped prevent carryover from sample to sample. And the SIM mode delivered excellent sensitivity with detection limits lower than 0.37 ppt. So SPME is another common way to analyze mold and odor compounds, and the way this works is a fiber is held in the headspace of a vial while the sample is being heated, and the fiber absorbs the compounds of interest, and then it's placed in the inlet and it's heated, and it desorbs those compounds. So compared to SPME, Purge and Trap is going to be a lot cheaper for a number of reasons. First, those fibers need to be replaced on a regular basis. They are specialized and expensive consumable. Purge and Trap is more automated, shorter sample prep and run times. We don't need to heat and run our samples for near as long as a SPME run does, and Purge and Trap offers greater system flexibility because you can run so many applications on it. Drinking water, wastewater analysis, it doesn't need a specific setup for just one application. All right, and now let's get into our Wisconsin GRO. So the analysis of Wisconsin GRO is vital in determining the composition and the origin of such products, including weathered fuels leaking from underground storage tanks or lust, spills in pipelines, and runoff from surface transportation. So for this method, we want to focus on a few areas, including cleaning up that sample pathway to ensure no carryover issues from sample to sample, and our methanol extractions for soil samples that are greater than 200 ppb. So we want to use our Atomx XYZ for this method, or if you have the old style Atomx, that works as well, because we want to be able to use one instrument to analyze our water samples, our low-level soil samples, and we want the instrument to do automated methanol extractions for our high-level soil samples, those being over 200 ppb. So first, we will go over the water method. So this method I created, it's basically all default parameters. I wanted to do this because I wanted all three of the methods to be about the same. So here are the standby conditions for the water method, and they're all default. So as soon as you open up to create a method, you should see all of these parameters already on there. All right, again, default is what I went for this method, but if you want a quicker analysis, you can run a 6-minute purge at 80 mils a minute purge flow rate, and that should be long enough to get all of your compounds purged out of your sample and onto your trap. All the default Desorb method parameters here. This method was done with a number 9 trap, so these are the Desorb temps that work well for that trap, and this is adequate Desorb time to get all of our compounds off the trap and on their way to the GC without transferring too much water. Again, default bake settings here, but if you are having carryover issues for this method, you can increase the number of bake rinses or the bake time and flow. But remember, this will just add more time to your analysis. So we found that there's adequate cleanup with the default parameters for this method. Here are the GCMS conditions. This method was ran with hydrogen as a carrier gas. So if you're curious about switching from helium because of the expense, then you can check out this full application note on our website. We used an 80-to-1 split to help with the moisture control. Remember, a higher split ratio means more of that desorbing gas coming to the inlets, going off to vent, and less of that is getting onto the column. So the higher split ratio means less water is getting into the inlet and onto the column. There's the trade-off with less of the compounds getting there because they go to vent as well. But we found a really good balance for this method at 80-to-1 split to improve our analyte recovery and moisture control. And I also want to note that this GCMS method was the same one ran for all three of our methods that we are building, the water, soil, and the methanol extractions. All right, here is the Wisconsin GRO water method tick for a 20 ppb. So we saw excellent peak shape and resolution with the method. All right, next we will go over the soil method. So again, chose mostly default parameters to try and keep all three methods the same. The automated soil samples are for low-level soil samples, so less than 200 ppb. The XYZ adds DI water from the reservoir to the vial and adds in the internal standards and the surrogates. The sample is then purged within the vial via the 3-stage needle, and then the sample is stirred during purge via the magnetic stir and the stir bar that you put in during collection. So in the purge parameter selection, it talks about mixing. So the type of mixing and the amount of mixing that we would need depends on the matrix of the soil. So fine soils such as clays might require longer mixing. So we might need to add in a premix before starting to purge, and longer purge times to ensure that there is adequate time for volatiles to be removed from the matrix. We also would recommend a less aggressive mixing. You could use the agitate mode so that you don't create a vortex and cause those clay particles to clump up and not get adequate contact with the water to remove the volatiles. For larger particles like sand, you can use a shorter mixing and purge times with a more aggressive mixing, maybe the medium or the fast mode. Humic soils require longer mixing and purge times in general because of the nature of the soil. They tend to vary so much from sample to sample because of the organic matter in the soil. It's going to change how it releases these volatiles to the water, and the mixing speed is dependent on specific characteristics of the soil. So in our purge parameters, the default dry purge is set to 2 minutes, but I did change it here to match it up with the water method to just half a minute of dry purge at 100 mils a minute. So with the XYZ's improved moisture control system, the moisture management is so efficient that we can reduce or eliminate the need for dry purge altogether. Therefore, with just a half-minute dry purge, we're still seeing adequate moisture removal for this method. And this innovation can get you anywhere from 1 to 5 minutes of time back per sample. So that's a huge time saver and increases sample throughput. But if you are having moisture issues with your soil method, feel free, 1 minute, 2 minute dry purge should be good. These are all the default parameters on the Desorb tab. If you are having carryover issues in the in-vial purge, you can add in extra methanol needle rinses to ensure that it's clean for the next sample too. And again, default bake settings here as well. Right, and here is the Wisconsin GRO soil method tick for our 20 ppb. And again, we're having excellent peak shape and resolution. Methanol extraction is a necessary preparation step for soils with higher concentration of the target compound, so greater than 200 ppb. Since these high-level soil samples need to be methanol extracted, and this adds time to our analysis. Utilizing the methanol extraction feature on the Atomx XYZ for high-level soil samples can save time and labor by automating the sample extraction process. Now, on the Atomx XYZ, you put your weighted sample. It's usually 5 grams in the sample vial with a stir bar, and just let the instrument do the work. It performs the extraction by adding methanol and surrogates to the sample vial. It mixes and it draws the extract, and then it dilutes that extract in water with the internal standards, and it purges it on the sparger, and it's analyzed just like a normal 5 ml water sample. So if the sample needs to be heated, there's a sample cup heater option as well, and of course the sparge heater too. Again, I kept these parameters pretty default just to align with our other methods. And here just need to change that desorb down to half a minute because the default is 2 minutes. And this default, it already adds the methanol needle rinse here, so helping out with the carryover. And default methanol glass rinse as well, to help with the carryover from sample to sample. If you need to increase the number of methanol glass rinses, and water bake rinses will help you with more carryover issues if you're having those kind of issues. Right here we have a tick of 7 replicates of 1,3,5-trimethylbenzene, methanol extracted high-level soil samples containing the final concentration of 50 ppb. So it's displaying excellent reproducibility at 6% RSD and 94% recovery. The XYZ has proved to be an excellent system to increase productivity in the lab. You can improve sample throughput by running multiple analyses in one schedule on the XYZ. By running this application on a single system, we saw MDLs as low as 0.15 ppb for the water method and 0.4 ppb for the soil method. We ran a midpoint verification check with precision and accuracy for the water method at 20 ppb, and so it displayed a 4% RSD for all compounds and an average recovery of 109%. We did the same on the soil side with 20 ppb soil samples, and we saw a 4.3% RSD, and we saw an average recovery of 95%. So furthermore, with the automated methanol extraction, we were able to process those high-level soil samples with an 88% recovery, and we saw less than 11% RSD over 7 replicates for all of our compounds except for one. When dealing with the high-level soil samples, the XYZ is able to use the methanol rinsing function to help control or eliminate that carryover from sample to sample. All right, next method we want to cover is 1,4-dioxane. So it's a solvent used in some industrial applications that can be found in drinking water. It's difficult to analyze because of its poor purge efficiency. Therefore, we need to focus on this purging efficiency sample introduction to the GCMS spec sensitivity, because we need to see at low levels, and sample cleanup to ensure that there's no carryover from sample to sample. Since this is usually found in drinking water, we can use our water's only Purge and Trap concentrator, the lumen. So as far as standby parameters go, these are all pretty default. As part of purge efficiency is our flow rate. So basically how many minutes and the amount of time we are purging and how fast, which is the flow. So a fast flow means that more purge gas is used in the same amount of time, and a really aggressive flow can cause back pressure issues and push compounds deep into the sorbent bed of the trap. We also want to look at purge time. So the longer that we are purging, the more purge gas we're using, and if we purge for too long, that can waste a lot of gas, one, and also push compounds deep into the sorbent bed of the trap. So therefore, as our purge volume and time are increasing, they get to a point where response just starts to plateau, and then eventually you start to lose response because the compounds are sticking to the sorbent bed of the trap, which can lead to a waste of time and gas, which means a waste of resources. Because we have no method restrictions here, we can do a quick analysis. We want this to be quick because of how difficult of a purger the compound is. We want to stick to our purge time multiplied by the purge flow rate equals to less than 500 or 500, If you stay in that range, you should be good to adequately get all your compounds to the trap. Also for this compound, we want to use our sparge vessel heater and heat up to 60 degrees C to drive that compound out of solution. Just remember, like I said earlier, the amount of water vapor that makes it onto the trap doubles for every 10 degrees C rise in sample purge temperature. For our desorb parameters, we have shortened our desorb time to 1 minute. If we shorten that desorb time, we do move less material to the GC, but we will have a shorter water peak. And the rapid increase of temperature during desorb preheat can drive that moisture out of the sample even more, and the final temperature of desorb ensures that that moisture stays out of our gas flow and that we transfer everything that we want to the GC. Also with this method, we have a higher split on the GC, which allows for this shorter desorb time. With our improved bake mode control, we can create faster flows and higher temperatures, which means that we can bake for less time, saving extra time per sample. So here we have an increased bake flow to ensure our sample cleanup. Here we have default Aquatech LVA method parameters for a 5 ml sample. Since the split is higher, you have a lot of flow to lower that desorb time. So a higher split can also help with moisture and improves separation and decreases broadening of peaks. We're also using sim mode in order to increase sensitivity because our calibration range goes as low as 0.2 ppb. And again, we are increasing that gain to create larger signals to see at those low levels. Here we have the results of our 1,4-dioxane method with a linear calibration of R squared equals 0.9996 for a calibration range of 0.2 to 50 ppb, excuse me. And here we have the sim mode scan of an ion 88 at our 0.5 ppb. To verify that the 0.5 ppb calibration point is precise and accurate, a reproducibility test was performed. The 7 samples that were prepared at 0.5 ppb displayed a 2.56% RSD with an MDL of 0.04. We were able to increase the purge efficiency of this difficult compound by decreasing the purge time, increasing the purge flow rate, and applying heat to the sample. The higher GC split rate allowed for a lower desorb time, pushing that sample off the trap into the GC, all while applying adequate moisture control. We achieved excellent sensitivity using the method parameters and utilizing sim mode on the mass spec. All right, last application we'll be covering today is Epichlorohydrin. It is a precursor chemical for many household products. It shows up in paper, plastic, insecticides, paints, varnishes. It's found in finished drinking water. It can react with chlorine and produce a carcinogen. And for that reason, it is regulated by the European normative 9883 EC with a maximum level of 0.1 ppb in finished drinking water. So we need to focus on these areas for our method development. For purge efficiency, we'll need to chill the sample because of how fast it breaks down. These calibration standards are also made in 10% weight by volume sodium chloride DI water to help with the purge efficiency as well. And we need since this is tested in finished drinking water, the method's created on the lumen. So all method parameters on this standby tab are default. For this method, we use the 10x1A, the 1A trap, which you can use dry purge for with that trap, but we didn't in this application note, just to highlight the lumen's moisture control system and how it can adequately remove moisture without the use of dry purge. But if you feel like you need to use dry purge, 1 to 2 minutes should be good. All right, and on the Desorb tab, we just want to lower those Desorb preheat temperatures and the Desorb temperatures to align with the parameters of our 1A trap so we don't break down the trapping material. And this is also true for our bake temperature, and we're increasing the bake flow as well in order to help prevent carryover from sample to sample. Here on the Aquatech LVA tab, we are increasing the number of bake rinses to 3, and that's again to help with carryover. So we have to be able to verify this compound at such low levels. Here we need to utilize sim mode and on the mass spec to significantly increase our sensitivity. And here are the results for epichlorohydrin. We saw 0.9998 R squared on the linear calibration for a range of 0.1 to 50 ppb. The lowest point in the calibration required by the regulatory body is 0.1 ppb. So to verify this level is both precise and accurate, a reproducibility test was performed. So 7 samples were prepared at 0.1 ppb, displaying a 8.25% RSD and an MDL of 0.024. To demonstrate the robustness of this method, 21 ppb check standards were also analyzed 5 days after the initial calibration curve was performed, and the average response of these check standards resulted in a 98% recovery from the original calibration value. When conducting drinking water analysis, it is imperative to achieve high levels of accuracy and precision to protect public health and safety. Detecting chemical impurities such as ECH is critical to the water supplier due to stringent regulations enforced by their governing body. By using the smart method parameters on the lumen, such as chilling the sample on the autosampler to reduce sample breakdown and preventing carryover from sample to sample, and utilizing sim mode on the GCMS, ECH was detected down to the 0.1 ppb level. Both the Atomx XYZ and the lumen have the improved moisture control fitting that increases sensitivity and extends routine maintenance intervals. Both have mass flow control, which is independent flow in all nodes, allowing for optimized flow rates during purge, dry purge, and bake. Higher flow rates means less bake time, saves you time in your runs. The trap cools 20% faster than other concentrators, so faster cool down means faster cycle times as well. The flexibility of the Atomx XYZ with the ability to run water, soils, and automated methanol extractions is unmatched by other sampling methods. Multiple analyses and matrices are possible in one schedule simply by changing the GCMS method if you need to. US EPA methods can be run right alongside each other, right alongside these other more specified analyses, specialized methods. With the Atomx XYZ, we can completely automate the sample preparation without compromising sensitivity, efficiency, and throughput can be greatly increased while saving time and money. So all of these app notes that I discussed today can be found on our website under the Resources tab. And if you want to see more webinars about purge efficiency and moisture control, we have all of our previous webinars on our website as well under the Events tab. And thank you so much for taking time out of your day to join me. Please check out our website for those app notes and webinars and to visit our online store. And you can follow us on social media too. Thanks.